directly onto the slide. A little bit more into the interpretation of results of microarray. This would be like an example output. Let's call the left target 1 and target 2, for example. If a spot on the slide is red, the target 1 successfully hybridized to the probes within the spot. If the spot is green, target 2 successfully hybridized to the probes on the spot. If the spot is yellow, they both hybridize to the spot, and in different levels. Like if it's orange, obviously there's more red. If the spot is black, nothing hybridizes to the spot. So in order to design these probes, we went through 3 main steps. First, we found representative sequences for all gene families. Second, we generated specific probes for each family. And then thirdly, we checked the probe specificity. In order to write this program, we used the Python programming language. It's a very verbose language, and one of the great things about it is it has already made BioPython modules, which are chunks of useful code for doing computation that are freely available, and you can just insert them directly into your program, so you don't have to write every single step. We also used MySQL, which is just a relational database management system, and that's used to run the Mycobacterium phage draft database. It's used to insert, update the information, and importantly to us, it's used to access the information. ClustalW, which I referred to earlier, is a multiple sequence alignment program. It's extremely complicated in the way it does its alignment, but generally it performs a pairwise alignment, generates a phylogenetic tree, which just takes into account the evolutionary distances between sequences, and then performs multiple alignment using this tree information. This is an output of a clustal alignment seen on JALView, which is kind of an add-on so that you can visualize the results. As you can see on this top portion, those lines of color are where all of the bases match. But towards the bottom, you can see that this alignment gets a little messy. And then at the very bottom is the consensus sequence, which is every base, whatever base was most common throughout all of them is made, and the consensus sequence here is a little bit rough because the sequences are dissimilar. We also use BLAST, which is a basic local alignment search tool. It's readily available online, and I've been using it in all my 4 years of college, and it's very, very useful. It simply looks for similar segments between the query and database sequences. So if you took a gene sequence, you just plug it in, press enter, and it would compare against the entire database that's connected to GenBank, and it gives you back what it matches. It also evaluates the statistical significance of the matches found, which is very important. Here's an example of the output. The top line is red, which represents the highest quality match. It's also almost as long as the query, so you can tell that this is a really good match. It has almost 100% query coverage. The bottom match, you can barely see, it's the little pink line. You can see this is a higher scoring match, and it also covers way, way less of the query. And again, back to the e-values, BLAST provides the e-values down there in the table. Now, the FamRater was very, very helpful in providing the organization into families in the first place. However, some of these families are quite large. Going back to that JALView, you can see that the consensus sequence is rough. And if we made a probe from that consensus sequence simply, it may not allow any hybridization of targets. So our program, one of the main goals is to subdivide those into subfamilies. So if you took family 7 and subdivided it into 7A and 7B, you can see the output for 7A is much more even. The consensus sequence as compared to the one above is much more even, and you're much more likely to allow probes to hybridize, targets to hybridize to probes if the sequence is as representative. And basically, from that consensus sequence, the consensus sequence represents this entire black line, and we would enter that consensus sequence into a program called Picky, which is also freely available online, which chooses an appropriate probe based on your inputs. And so an example would be this little chunk of purple would be the probe, and the little chunk of gold would be the probe. And those would be the spots put on the slide. So there would be 10,000 of those little guys. So in order to do so, this is the general flow of information for our program. It first gets a family from the Mycobacterium phage draft database. It creates a phylogenetic tree using ClustalW. Then using the BioPython module called Philo, it accesses the name of the root of that tree, then accesses the name of the sequence of the closest relative, grabs them both, and using a retooled FamRater code, runs BLAST and clustal alignment on them. If the score meets the threshold, this means that they are similar enough to remain in our family, and so it goes back and grabs another.